research fellowship during his PhD.
Yeah.
Over to you, Kiran.
Yeah, thanks, Praneeth. I'll mainly talk about the sort of things I've been doing for the past 1 year. So it's not related to the things I did before. Yeah, so since it's already late in the day, I'll keep the talk pretty light. But feel free to interrupt me at any point if you have any questions. This topic might be a little different from the other talks you guys have heard. So it's 20 years of Microsoft Research India office. Yeah. So yeah, today I'll mainly speak about large-scale retrieval. Which I've been doing for the past 1 year. So it has a very nice story. We initially started out doing some theoretical understanding of this topic, and over the past year, we have been able to use this understanding to develop many practical algorithms for new problems that came in. So basically, I'll be telling about this story. So this is in joint work with MSR, many folks from MSR, mainly many RFs within research fellows at MSR, product teams, and few academic collaborators. Okay, so let me begin by introducing you to this retrieval problem. In the retrieval problem, basically you have a huge corpus of objects. Okay, and given a query, you want to quickly parse through these objects and return the objects which are relevant to the query. Okay, so this is a very general definition. It's being used everywhere. For instance, when you type in a query in any search engine, the objects are basically websites, and given the query, we try to find the relevant websites in the case of search engine. Even in the case of ad recommendations, we look at the query the user has typed in, and here the objects are ads, and we retrieve the relevant ads to be shown to the user. And this problem became even more popular in the recent days, mainly because of the RAG part of LLM. So when you ask LLM a query, it first does a retrieval. It first goes and fetches relevant information and uses this relevant information to answer your query. So this top answer is the answer given by Copilot, which is a LLM generation using RAG. Okay. So one of the popular approaches for doing retrieval is something called as dense retrieval. So what is dense retrieval? You have these objects. As you saw earlier, these objects could correspond to documents, ads, or anything else. So given these objects, the first stage of this dense retrieval is that it embeds them into a high dimensional space. It embeds each object as a vector in some high dimensional space. Okay. What is so nice about these vectors is that similar objects get similar embeddings, meaning all the animal images will lie on one side, all the car images will be on the other side, and so on. They are close in some distance metric which you have decided during your training phase. Okay, but the most popular distance metric used is the Euclidean distance. Okay, so once you have done that, now a query comes in. The query is also embedded as a vector in this same high dimensional space. Now, given a query, the relevant objects are basically the ones which are near to this query vector. Okay, so now the second stage basically boils down to, given a query vector, you want to design a data structure which will quickly retrieve the nearest vectors to this query. Okay, so that's the second stage. Now, of course, you can do a linear search, but the number of websites is around 10 billion. How will you do a linear search over that? So you want to quickly pass through and because you want to quickly do it, you can only hope to get some approximate nearest vectors, not the true nearest vectors, but they still suffice for all the practical application. Yeah, so it depends. It ranges from 100 to 1500 dimensions. Even 3000. I think the new OpenAI embeddings might be 300K dimensional vectors. I'm not sure. Sorry, 3000 dimensional vectors. Yeah, not 300K. Okay, so in today's talk, I'll be talking about both the stages, but primarily on this data structure stage. But I'll also mention one brief work that we did in the regarding the embeddings also. But this I'll just flash one slide for this work. But I'll mainly talk about this data structures part. Okay, so let's come to the vector search. So this vector search is also called as nearest neighbor search, as you saw. Since we'll be computing approximate nearest neighbors, it's also short form as ANN. It's popularly known as ANN. Okay, so this problem is a very fundamental problem in computer science. People have been studying this since 1990s, maybe even before that. But there are many papers giving some nice algorithms date back to 1990s. And currently the popular algorithms for this problem broadly fall into three categories. One is this local sensitive hashing, which is the first provable algorithm for ANN. So people even teach this in topics course in data structures these days. Okay, so this is one of the very popular algorithm among academic folks. But it turns out in industry, people favor these other two class of algorithms. The second and third are basically these clustering based algorithms and graph based algorithms. And both these algorithms, they were mainly heuristic algorithms, but they performed very well in practice. And most of the industry algorithms were based out of these two categories. Yeah.
Is there any insight into why like academicians focus more on locality sensitive hashing?
Yeah, mainly because you could show some nice theoretical results. Initially, they could show some nice theoretical results for that. So initial LSH approaches were data independent. So they were data independent, and then yeah, mainly because they could show some nice guarantees about these algorithms. In clustering, it's mainly you just do k-means. It's more like you just do k-means and you go through the centers, first identify the center which is closest to the query, and then go within the cluster and explore. It's a very simple heuristic algorithm, but it seems in practice it does very well. But proving nice guarantees for clustering is very tricky.
Maybe another way to ask the question is, what is the property of the usual data which makes these approaches very well suited for practical data? So do we have insights into?
Very little insights. So today I'll talk about one property of the data set, which was very quantified very recently, which tells if data set has that property, graph-based algorithms do very well on that data set. So today I'll talk about such a property. Yeah. Okay, so this graph-based approach, in fact, the Microsoft has a algorithm called DiskANN. It's very popular. It has had a huge impact within Microsoft and across outside Microsoft as well. So many of the Microsoft products have been powered using this DiskANN algorithm. It has led to a huge savings in various aspects. In fact, not just within Microsoft. These are some of the startups which offer vector search feature. Their primary thing is vector search, and in fact, they write on their blog post that their algorithms were inspired by this Microsoft's DiskANN algorithm. So roughly 3 or 4 years back, I might be lying here, but one of these startups was evaluated at 700 million. So it might be close to $1 billion now. So it's a very important problem, and for people who are interested, there is also a computation track. If you have your own algorithm for vector search, you can just go and submit here and try to get into the leaderboard. You might also have a $1 billion startup if you do that. Okay. So seems like we already are in a good stage in vector search, right? We have an algorithm. There is a lot of work has been done in this vector search world. So a natural question to ask is, yeah, what next in this particular field? So first of all, as I said, the most popular industry algorithms lacked theoretical guarantees. We didn't know, we had an intuitive understanding of why they work, but not a good theoretical foundation. So the initial goal that we started with was this first point, to have a good understanding of why these algorithms work. And also it turns out in these modern ML applications, they are asking for something, not just relevant objects, but something more than relevant objects. For instance, you just don't want relevant objects to the query, you also want diverse objects which are relevant. For instance, if you type in the word jaguar, you just don't want to retrieve animal images or car images. You want to retrieve both animal and car images. You want diverse set of images. I'll give you one example of why diversity was needed for us, which was very critical for us. But there have been many studies which show that diversity in search actually enhances user experience and it leads to quality output. So right now we just don't want relevant results, but also diverse. Also earlier objects were embedded as points in some single points into some high dimensional space, but the embeddings are also evolving. Now one object is embedded as 100 vectors. To capture much more fine-grained information, they are embedded into more number of vectors. So how do you design ANN algorithms for that setting? Also, there are other settings such as filter search, online search. We are getting these documents in an online fashion. How do you update these ANN index, and many more new questions which make sense in practical setting right now. Yeah.
You're saying if it's embedded into 100 vectors, isn't it the same as like considering like a higher dimensional space instead? Like what's the...
Say that again. I didn't hear.
One object is embedded to several different vectors. I mean, first of all, metric is like gone, right? Like D.
So one object in the multi-vector setting, is it?
Right.
Yeah. One object is, let's say, embedded as 100 different vectors. Yeah.
Okay.
Yeah. So I'll tell you how do they define similarity between query and a document using these 100 vectors. I'll tell you, but all I wanted to say was to capture much more information. Just representing the whole document using one vector, we were losing a lot of information about that document. To capture fine-grained information, people have started embedding them into multiple vectors. So that's what the multi-vector problem is. I'll define in a much more formal way what I mean later in the slides. Okay. So given these new requirements which are critical for the modern applications, we want to ask, can we build these vector data structure to these new problems, new requirements as well? Okay. So I'll mainly talk about diversity, but I'll just show you one slide on each of these other topics towards the end of my talk. So just to summarize, what are the two motivating questions? We wanted to build a theoretical understanding of disk NN and use that understanding to design algorithms for these new requirements. So that's how we started with. So let me start with the theoretical understanding part. So this work was in joint work with some of our RFs and Ravi Shankar, who is a colleague at MSR. So this is published in ICML this year. So let me start this section by giving you more details about what is a graph-based method. Okay. So in a graph-based method, there is a corpus of these vectors now. Objects are embedded into vectors and we have corpus of these vectors. The first stage is you take this vector data set and build a graph. Okay. These nodes in the graph correspond to these vectors, and these edges somehow they are supposed to capture the similarity between these. They capture these edges are added keeping in the distance between these vectors in mind. I'll give you more details on how these edges are added, but the nodes here are vectors, and edges in some sense capture the similarity between the vectors, which is given by some predefined metric. And then in the second stage, which is the search stage, a query comes in. When a query comes in, what do? We start at a query comes in, which is placed here. If we start at an arbitrary some start node, some predefined start node in practice, and then we just look at its out neighbors. Okay, so it has 3 out neighbors. We just go to the point which is closest to the query among these out neighbors. So among these 3, if you notice that this node is closest to the query, we move here. Again, we keep repeating. We look at its out neighbors and notice that this is closest to the query, and we just move here in the next step. Okay, so this is the greedy search. So this is what we do during the search time. Okay. So now what is so usually in these vector search world, the number of distance comparisons is what matters us. How many distance comparisons that you did. So here, while moving to the out neighbor, I computed 3 distances and I did one more distance comparison here. So it's as good as doing linear search only, but among these 5 nodes. But we'll show you that in actual, this does far lesser number of comparisons than the linear search. So what will be the rough running time of our algorithm? What will be the number of distance comparison? It's roughly approximated by the average degree of this graph and the number of hops that it did. Okay. So because of these two, what is a good graph? The good graph is one which is sparse, meaning it has low degree, but also it has low diameter. Okay. So we'll try to construct graphs which have these two properties. Okay. So yeah. Yeah, it will be fully connected. Yeah, because if it is not, in practice, it will be fully connected. If it is disconnected, it's a very bad graph for us because some of the points become unreachable from the start. Say that again.
It sounds like you can put this in a nice framework and say, okay, this is what the number of degrees should be.
Right.
Should be.
Right. Those are the sort of results we will show. Yeah.
Points, when you embed them into that graph, do you also store the original embeddings, like to compute the distances?
Yeah. We need to store the embeddings. Okay. So storing the embeddings is very expensive. So right now we also work on data compression algorithms. So how do you efficiently store these vectors and so on? But it's a completely different topic than this. But to compute distances, we need those embedded vectors. But how to efficiently store them, how to compress them is a slightly different topic than what I'm going to cover today. Yeah. Okay, so let me just quickly summarize what are some desired properties of this graph. As we said, we want low average degree and we want low diameter. But we missed out one important property, right? It should reach to a good solution. It's a local search algorithm. It should reach to a very good solution also. So let's say, so it should reach to a good approximate solution. So let's say a query came here. What is the nearest neighbor? V is the nearest neighbor. So we are at S, start node S, and we want to reach V. What we can do? We can directly add an edge from S to V, right? Then we know that we'll definitely reach a good solution. But if we keep doing this for every query, we'll end up constructing a complete graph. Okay? Because I can always pick a query which is close to any vertex. So if I always keep adding an edge from the start node to or a star graph, or if you want connectivity between all pairs of vertices, you end up creating a complete graph. This is as good as doing a linear search only. So it's not nice. So how do we tackle this? So we want to eventually reach V. So directly adding an edge from S to V will increase the degree. Okay, so what will we do? So instead of adding an edge from S to V, we make sure that we always added an edge from S to some vertex which is close to V. This is what we try to do. Okay, so for instance, we added an edge from S to T. This edge can be used to reach T, but also can be used to reach V. So what is the definition of close by? So you should have an edge from S to T, which is within this ball. What is the radius of this ball? This radius of this ball is 1 by alpha factor of the original distance you were far from. So the radius of this ball is 1 by alpha times the distance between S to V. You were at S, you know that you have an outgoing edge, which will make you a multiplicative progress of 1 by alpha. Yeah. A good value for alpha, you just do trial and error. You play with different values of alpha. But right now we realize something like 1.3, alpha value of 1.3 works very well in practice. So you will see that if you keep, so what happens if you increase alpha? The radius of the ball is coming down. It's as good as adding an edge from S to V directly. So if you increase alpha, you'll guarantee a very good solution. but your degree of the graph will increase. So somehow you need to balance them both. And the way people do it in practice is just try out different values of alpha and pick the one which does the best. Okay, you can see that why did we define such a thing? Because we'll make a multiplicative progress in each step if we make sure. So these graphs are called as alpha reachable graphs. Okay, so what is the alpha reachable graph? Between any pair of vertices. Here we are considering S to V, but between any pair of vertices. So there should exist an edge from S to T. There should exist an edge from S to T such that the distance between T to V is at most 1 by alpha times distance between S to V. Don't overthink about this equation. All you need to know is that by S has an outgoing edge such that it will make a multiplicative progress of 1 by alpha. That's how you should think about this condition. Okay. So if you keep repeating this condition and notice that the graph you end up constructing will be, in this particular case, it will just be a line graph. Here, I mean, I created such that I didn't want to create a complete graph, so I created a line graph. But you can just see that between every pair of vertices, you try to do this. Basically, for instance, yeah, maybe we might need to add an edge from S to V because of B or something. But yeah, I have not given you distances. Let's say the distance between this edge from S to T also serves, will make a multiplicative 1 by alpha factor progress by for moving from S to B also. Assume that also. So is the alpha reachable condition clear? Yeah. It's a very simple definition. It's my mistake if I didn't explain it well. So it turns out if I construct a alpha reachable graph, the degree of this graph is at most alpha to the power D. Okay, it depends on alpha. As you can see, it increases with alpha. Now, what is D? D is something called as the doubling dimension of the data set. Okay, so this is one of the characterization of the data set, which tells you that if the doubling dimension of the data set is pretty low, then this graph will have very low degree. And generally in practice, we believe that this doubling dimension will be pretty low. That is the assumption under which these graph-based algorithms work on. Yeah, so let me see if I have a slide. Okay, I'll write it on the board.
One more question.
Yeah.
There exists a graph, alpha reachable graph with maximum degree less than or equal to this, or any alpha reachable?
So a complete graph is alpha reachable.
Have much higher degree.
Much higher degree. So there exists a graph which has such a low degree.
And we can construct it efficiently.
We can construct it efficiently. Yeah, that's the statement. So what is the definition of a doubling dimension? So let's say you have vectors v1 up to vn. So now I have to tell you the definition of the doubling dimension of this. So take any vector vi. Take any vector vi, look at the ball of radius r around vi. Okay, so just look at the ball of radius r around vi. Look at all the points which lie in this ball. So now I want to cover all the points present in this ball, but I am allowed to pick only balls of radius r by 2. Okay. So the number of smaller balls of radius r by 2 that are required to cover the points in the larger ball. The log of this is the doubling dimension. Okay. So it's a little technical definition. Max over all, so max over all Vi and R. Yeah. Yeah.
R by 2 balls have to be centered on?
No, they need not be. They need not be. Yeah. Yeah. But only some constants here and there change. So that restriction might not be. Regardless of what is the order here? Yeah.
It's a bigger ball.
Yeah. Then R by 2 will remain. Yeah. Smaller ball is also. I mean, if you choose R such that only one vertex belong to that, one vertex belong to that ball, then I'm saying the number of balls of radius R by 2 to cover the number of radius of size R. Even if you choose R, you will have higher R, you will have more points to cover. So even if your R by 2 ball became larger, still you might require large number of balls.
Max over VI and R.
Max over VI and R, and it is not. What won't increase? Yeah. Correct.
That's a max over.
Correct. Smaller ball also. Right. No, it won't go to infinity, right? Because you can always find, okay, when I'm trying to find a ball of radius, see, I only need to cover points which are there in these points which are covered. So only, let's call this set V. So I only need to cover V intersection this ball. So I only need to cover the points which are present in this ball. So you pick anything, you can always pick smaller balls centered at these points. At most n number of balls is needed. So the doubling dimension is always upper bounded by log n. Because I can always pick these smaller balls centered around at each of the points. If these points lie in R to the power D, then the doubling dimension will be, yeah, I think O of D or something. No, it's not centered. These need not be centered. These are centered around vertices, but if you don't center around vertices, let's say you pick something, if this set is empty, then your these smaller balls don't need to do anything. I'm saying you have to cover, all you need to do is cover the points among V1 to N which have an intersection with this ball. Anyway, that definition and showing that definition and this I'll not be doing today. Yeah, can I come back to slide? How do I come back to slides? So, okay, first of all, I forgot to mention. So this was shown by this was shown by Piotr Indek and Heike Shu, who is a student of Piotr, who is a prof at MIT. They showed this. So mainly, this is a very sweet paper, and this has sort of has given us the foundation to think about these graph-based methods. Okay. So
maximum diameter.
So log of the aspect ratio of the data. So there are some other terms here. I didn't want to focus too much. They are not so important, but the diameter of the graph is log of alpha, right? In some sense, log to the base alpha, because you are making multiplicative progress of alpha. Diameter, there are these aspect ratio of the data comes here. So there are some other terms, but that is not the main important focus. This base alpha is the thing which I wanted to focus on. Yeah.
I guess can find a shortest path will be of this, but diameter could be potentially much larger.
So diameter itself will be log of alpha to the base alpha, right? Because this alpha reachable property is between any two pair of points.
So even a complete graph will satisfy the alpha reachable property.
Correct.
This particular construction, but its diameter.
It's the complete graph has diameter 1. And diameter 1, but like degree is. Huh? Say that again.
So diameter is the shortest.
Yeah. So diameter is the max of all pair shortest paths. Yeah. So the diameter of the complete graph is 1, but its degree is n. So this is somehow trying to get the balance right. Okay. So now let's try to, so we defined what is alpha reachable graph. Now let's try to understand how good are the local optimum solutions. So we'll be doing this graph traversal. At some point we'll get stuck somewhere, right? We'll not make any progress. Now let's try to understand how good those solutions are. So let's say we did this traversal and got stuck at yes. Okay, we did some traversal and got stuck at yes. Queries here, the best solution was V, but we got stuck at S. Why did we get stuck at S? Because its out neighbor is T, and somehow by moving to T, we might not be making any progress. What does that mean? That means that the distance between S to Q is less than or equal to distance between T to Q. Though here T is visibly closer, but if it gets stuck at S, it means that the distance between S and the query is already less than distance between its out neighbors, and T is one of its out neighbors. Is this clear? So this is the condition. If S is a local, you just look at its out neighbors and you are not making any progress. I want to find the closest neighbors and I'm not making any progress by going to T. I'm only increasing the distance by going to T. So that's why I'll get stuck at S. But T has a nice property that it satisfies this alpha reachable property which we defined earlier. So we get these two inequalities. Okay. Now, what will be the approximation ratio of this? What will be the approximation ratio of this local optimum solution? That is what we want to bound. What is the approximation ratio? We returned S, whose distance is d of S comma Q, but the optimum solution was V, which is d of V comma Q. And their ratio is the approximation ratio of my local optimum solution. And I try to maximize this approximation ratio or all possible vectors and all. Okay, that will be my worst case approximation ratio. Pick any query you want, any possible configuration of vectors such that these two conditions are hold, and you try to maximize this. That is my worst case approximation ratio. Okay, so it turns out, okay, basically I'm rewriting this, and D cannot be arbitrary, right? So D should be a distance metric. So if D is a distance metric, this is the optimization problem I get. This is a factor revealing optimization problem. And it turns out the maximum value of this is at most alpha plus 1 by alpha minus 1. So this was shown by Indikshu. Okay. Alpha plus 1 by alpha minus 1. And the running time, as I said, will be alpha to the power d into log alpha, which is just the average degree times the diameter. Okay. So this is the approximation ratio you get. As you can see, if alpha tends to infinity, your approximation ratio is going towards 1, which is good. That is over S, V, Q, and also T. And even you can put over D also, any distance metric you want. Even then, it is just alpha plus 1 by alpha minus 1. No assumption on the distance metric. Okay. So now I'll just tell you this very sweet observation which has led to what we did. So we wanted to reach from S to V, right? That's why we drew this ball. Now there are so many possible candidates to add an edge to. We could have added an edge to T, we could have added an edge to A, we could have added an edge to B. Still, we would have made multiplicative progress. So which one will you decide? So will you go with adding an edge from S to T or S to B? Okay, so it's a, yeah, I mean, somehow people thought it will not make any difference. But it turns out that this makes, yeah, it makes a lot of difference. So what is the difference between these two things? So here T lies between S and V. Okay. In this other case, T, yeah, like V lies between S and V, basically. That is the only difference. Okay. So we call this a graph which satisfies this, where you add an edge to a T, which lies between those vertices S and V. So this is we call as alpha sorted reachable graph. Earlier it was alpha reachable. This is, you include this sorting property when you are adding this edge. So earlier, we had this, so we make sure this is the new constraint we got. The distance between S to T should be less than or equal to S to V. This is the new additional constraint. In that optimization problem, I'm just going to add this additional constraint, nothing more. Okay. So let's add this sorting property condition. It turns out by adding this condition also, you don't really get an approximation, better approximation ratio for arbitrary metric. But for Euclidean metric, which is the most popularly used metric, we get better approximation ratio. Okay. So the worst case, you can now show that if D is a Euclidean metric, this approximation ratio turns out to be alpha by alpha minus 1. Okay. So just for the Euclidean metric. So also the previous works, there was no paper so in practice, you don't just request one website, right? You request hundreds of websites. So there was no analysis on how good are these 100 vectors which were retrieved. So that is called as a beam search, where you retrieve not just one, but many nearest vectors. In this paper, we also give approximation ratios for this beam search setting. We show that in the Euclidean metric, if you do a beam search on alpha sorted reachable graph, you get alpha by alpha minus 1. Each individual point, each 100 points are alpha by alpha minus 1 approximation to their true counterpart nearest neighbors. We show a very strong result. But for the worst case metric, it is still alpha plus 1 by alpha minus 1, and all these results are tight. Yeah.
Yeah. What other metrics were considered?
What were the metrics considered?
Besides Euclidean, were there any non-Euclidean metrics?
So, I mean, here to show approximation, worst case approximation ratio, you can consider L1 metric.
Okay.
L1 metric. But here we are saying for any metric, we get this. But for Euclidean, or specifically for Euclidean, you get a far better approximation ratio. That is the punchline here. And somehow people were doing the right thing to embed them into Euclidean metric in the first case because it has a better ANN algorithms for that case. And I want to say that for some other metric, there might be better algorithms. Okay. Yeah.
Suppose for each query, you also had the probability with which it occurs. Can you come up with better kind of structure?
As better expected approximation ratio, let's say. No. So there are no query dependent results known. So this is all query independent results.
Sure.
We don't assume anything about query distribution, but there is no work on this.
It's well motivated, right?
It's not well motivated. So these are high dimensional vectors. So this Q is also high dimensional vector. What distributional assumption do you make about Q is unclear.
To get relative probability. Some are important, some are less important.
Yeah. Yeah, some are important and some are less important. I see. I mean, some queries are more frequent and some queries are less frequent. Yeah, I mean, yeah, even haven't thought about this question yet. So I don't have a good answer, but there is no literature on what you just asked as of now.
One more question.
Yeah.
So when we are doing beam search and retrieving multiple things,
yeah,
can we hope to get a better approximation ratio?
No,
because
no.
like we'll have potentially higher recall.
Yeah, no. I mean, in practice, we do that, but you can always construct a graph, handcraft construct a graph, put 100 points on that local optimum solution where you are getting stuck, put 100 copies of that same point, and you have 100 list and all of 100 of them will get stuck at the same point. You can cook up some theoretical examples where you increasing the list size doesn't necessarily increase the approximation ratio. But in practice, we do observe that increasing the list gets us better recall and approximation ratio in practice. But you can definitely cook up some hard things.
So these both are the asymptotic type ones, right?
So here, this is a fixed approximation ratio. There is no asymptotics here, but these running times which I described here, these running times are asymptotic ones. Yeah. So now you can ask, did this sorting property was just a theoretical gimmick or did it have any practical importance? It turns out, if you sort them and add versus not sort them add, you see there is a clear difference between the recall. So what is the y-axis? Y-axis is how good of a solution is, which is measured through recall. You don't need to know that. Higher the number, better the approximation ratio is. And you can see the blue curve is the sorted one and the red curves are the unsorted ones. And you can see a clear difference between sorting and not sorting. Yes. Arvind.
So that sorting is in the graph construct.
Correct.
What
Correct.
describe
Sorting
that?
is sorting is in the graph index building stage, which is the graph construction stage.
And you can do it easily. Like there's no overhead.
No. You can do it easily. Yeah. You don't need to do anything additional for that. Okay. So let me just give you one slide proof for this. Yes.
You just said that it's like in the initial phase, but then like suppose a new query comes, do you like add edges to the graph?
No. So this is, as I said, this is query independent. Given these vectors v1 to vn, I'll construct the graph and I'll keep it. And I'll not change this graph. Your query can be anything. The graph remains the same. I'll still be doing the search on that graph. And for all queries, I always have that worst case approximation ratio.
Use a selected set of queries to construct the graph initially? Or?
No, we don't consider. So it is query independent. Because the alpha reachable property is defined only in terms of VIs. So it never took query into consideration. So doing something query dependent is a very interesting question. Which is very less studied, as I said earlier. After the initial construction, can we add a VI point? Yes, I mean, that's a very good question. That is the online question. It is called online vector search, meaning your vectors are coming in an online fashion. They come, some of the vectors get deleted and so on. It's a hard problem, but there are very good practical solutions to it. But we don't have any theoretical results as such for that problem. But in practice, we do add new vertices, we delete new vertices. There are some heuristic algorithms based out of this theoretical understanding. Okay.
Can you think of adding like some Steiner points?
Where is this?
Here you are adding for every vertex in the initial construction. Like
very good question, Arvind. I don't know how Steiner points help, and that's a very I don't know. So nobody has studied these questions. But you need to add very few Steiner points, because if you add like n Steiner points, or like it will be huge blow up in memory. So there are many practical constraints. You don't even have space to store these vectors. But if you can add a few Steiner points and help the graph search, it will be a very nice thing. And showing something theoretically also will be very interesting. Okay, so let me give you one slide proof of this result. So earlier we had this optimization problem which I wrote, right? Which is a factor revealing optimization problem. I just added this new constraint of sorting property. But for Euclidean metric, note that these are, for the Euclidean metric, it translates to this. You can just take a square of these things and you get this. So does this look familiar to anyone? What this optimization problem is? Meaning it doesn't have a name, but what kind of optimization problem is this? It's a semi-definite program. You can rewrite it as a semi-definite program basically. So it's an HDB. So you can just do to show an upper bound on the optimization problem, just take its dual and show a lower bound on its dual. So you just use, it's a SDP, you just use weak duality and construct a solution for its dual to show an upper bound on the primal SDP and to get that alpha by alpha minus 1. But constructing the dual solution was the tricky part. And beam search takes a lot more effort, but I'm not going to talk about that beam search here. Okay, so we now built a good theoretical understanding of this. So I should end 5 minutes before, is it, or how?
Yeah.
Okay.
What is the algorithm to actually construct that graph?
So right now we say this, but it's a heuristic algorithm. We apply a lot of many heuristics on top of this. But consider a vertex, sort all the other vertices based on the distance. You add an edge from the first word to the first vertex. Okay. Then you see to whom all you don't need to add an edge anymore. And then you will see that to the second vertex, you don't need to add an edge. Your third vertex, you don't need to add an edge. Then you go to the fourth vertex, but now you need to add an edge. To the fourth vertex, you go and add an edge to the fourth vertex. But this is an n square time algorithm, so it's not very practical. So we first go and pick a candidate list to whom we are going to add an edge. Rather than considering all n-1, we first go and pick a small candidate list. This candidate list will be contains some 10,000 vertices. Instead of 1 million or 1 billion, it will contain 10,000. Among these 10,000, I'll just run the algorithm which I described to you. Okay, so so we studied a good theoretical understanding of this graph-based algorithm. So what was our second question? Use this understanding to design vector search algorithm for the new requirements. What were the new requirements? Diversity, multi-vector, and filter. Okay, so notice that I can always use the naive algorithm to solve all these new features. What will I do? Let's say I want 100 nearest vectors satisfying diversity, some diversity constraint. Okay, I want 100 nearest. What I can do is, one of the popular approaches in practice is, instead of fetching 100 vectors, you just go fetch 1000 nearest vectors first. On this 1000 nearest vectors, you just run some brute force algorithms to pick the top 100. This is always a possible algorithm, and many of the algorithms are of this post-processing. So you can just take this 1000, among them you pick top 10 based on your requirement. This is the most easiest way to handle this. But in this case, we will find algorithms that do better than this post-processing step. Yes, Arvind.
So this particular brute force, like if you want 100 from 1000 and this diversity is some function of your chosen set, then it's like 1000 times, whatever, 1000 choose 100, right? That's not.
Yeah. I mean, not brute force in that fashion, but some algorithm, polynomial time algorithm. But all I wanted to stress is you have to only look at 1000 vectors to solve this problem. But you can define, so it really depends on this definition of which I'm considering, right? So, but the definitions we consider, we can actually compute the best 100 in polynomial time. And we only care about such definitions, right? But you have to go through 1000 choose 10, then it's not a very good definition of diversity for us. Otherwise, you can do some approximation algorithm. But the point is that from 1 billion, you came down to 1000. Now you can afford to spend more time. That's the point. And this is the one thing which people use in practice. Yeah, post-processing is technique. Ideally, you wanted 100 nearest diverse vectors, okay? But what I will do, I don't know how to get 100 nearest diverse vectors. I'll just use the naive vector search algorithm. I'll go first fetch 1000 nearest vectors, just 1000 nearest vectors. On those vectors, I'll just go and do diversity. Yeah, using some brute force or some algorithm. Okay, so yeah, for this problem, yeah, I'll just talk mainly about diversity. I have only talked to give motivation and not really about the algorithm. Yeah, so this is also with a bunch of academic people and MSR people, and also product team. So this came out of the product team. This problem came out of the product team. It's very nicely motivated. It also appeared in ICML this year. So what is diversity in search, right? As I was telling you, if a user types in the word Jaguar, if you go and see Bing results, they all contain animal images. And there is no Jaguar car image. And Google mentioned that they had induced diversity into their search results. They've made a big announcement about introducing diversity. But even for some of the queries, like for instance, if I type in transformers, there is no LLM, though it's extremely popular, it's not being picked.
These results are being searched when actually?
Search when?
Yeah.
In 25, very recently. No, very recently. Yeah. So, yeah. So, and generally, yeah. And also in RAGs, let's say you want to write a 2-pager on the, okay, I need to change this to ICTS. I, yeah. So we want to do diversity on different authors, different timelines. Let's say I want to talk about the history of an institute. I need to look at their research across different years and all to write the history, right? So there is some notion of diverse search would help to answer such a question as well. Okay, and there are a lot of recent articles which are coming up talking about importance of diversity in results. But what I will talk today is what motivated us to look at this problem is diversity in ads. So this is the ads which is shown by the Bing system. So if you type in the word dress, notice that all the sellers, there are only 2 sellers which are being picked, only Myntra and Jockey India, and these are the big sellers. So a lot of the small companies were very unhappy with us, saying, "Hey, we are ready to pay you, show our ads," and somehow most of the times we are just displaying ads from the these big sellers. Okay, so somehow they asked us, "Hey, can we output diverse set of sellers when we are displaying dress?" So this was the initial motivation for this line of work. So this, yeah, as I said, it was to retain these small sellers who were complaining, and also this is some sense advertiser fairness, right? Ideally, you should show ads from all possible sellers. And also, in some sense, people believe that increasing diversity helps with the user experience itself. Yeah. So then the question boils down to, can we build a data structure to support vector diverse search, which does better than the post-processing step, which I told you earlier. So now, yeah, what to capture that, what should be the definition of diversity, right? So that many different sellers are coming up. So as you saw, based on different examples in the web search, the definition could be very different from the context of it. So it actually depends on the context. The definition of diversity depends on the context. And today I'll talk about a very simple definition. Though in our paper, we talk about a much general definition of diversity and all. So earlier objects came with just relevancy vector, right? Just relevancy vector VI, but now they come with this seller information also. Color, let's call that color for now. Okay. So an object could be dress, could have colors saying Amazon. Okay. So this color is an indicator of the seller. So a query comes and we want to retrieve 100 relevant objects. Okay. And the diversity, the way we force diversity is that at most 10 objects can come from one particular seller. Okay, this is a hard constraint. We added a hard constraint saying, oh, retrieve 100 nearest neighbor, but make sure you pick at most certain things from 10 objects from one color. So this is a hard constraint. We now there is a new work on using Nash social welfare to definition of diversity. This is in joint work with Siddharth Burman and his students at IIC, but it's still ongoing effort, so I'm not going to mention it in this talk. So this color could be seller or timeline or topic, right? So as I said earlier, and our definition of diversity is enforced through this hard constraint. But so now in 1 minute, I have many other slides, but I'll quickly mention the important ones. So here this object has blue color, this has a orange color. So a query comes and it asks us to retrieve 2 objects of different colors, let's say. I mean, here the hard constraint is that you are allowed to pick object of at most 1 from each color, so which is equivalent to retrieving 2 objects of different colors. So what is the optimal solution in terms of diversity? You have to pick T and you have to pick A, right? Given this query, the closest blue vector is T and the nearest vector is A. If you do naive greedy search, it will get stuck at T only. So we'll just return or it will get stuck at T and V because you are requesting two solutions and you'll return T and V. It is not a good diverse solution. But somehow we need to change the search algorithm itself. So we introduce a new diverse search algorithm. So which makes sure while searching itself, it makes sure that you keep diverse solutions in your output. But just introducing diverse search, even the graph also needs to be changed. By just introducing diverse greedy search, we found that you really cannot get good optimum solution. Some of the colors which are the true optimum, they might not even be reachable at some point. So we need to change the graph also. I'll not have time to tell you how we construct this. But even for this, so this construction, this graph construction and the greedy algorithm comes from that theoretical, this alpha reachable property, which I described earlier. It comes from that. But to handle diversity, we have to increase the degree of the graph by a little bit. So that is the overhead you pay for handling diversity. Okay. So yeah, forget about all that. So this left-hand side pie chart is the seller distribution of our ads. Like you can see that all the ads were coming from just few sellers. When a query came in, we ended up displaying ads just from these 3 or 4 sellers we had. So that's why diversity was very important. There were many sellers where the number of ads they were displaying were very few, and we never ended up picking them. As I said, so this green curve is the post-processing algorithm, and this blue curve is our new algorithm. As you can see, the blue curve is quite below than the blue curve is doing far better than the green curve, which is the post-processing which I described earlier. Okay, multi-vector I'll skip, and other things also I'll skip. Yeah. There is a
Slides will be shared.
yeah. I'll send you the paper only. So multi-vector, as I was saying, for a document, earlier you generated one single vector, but now for each word in the document, for each token in the document, the transformers generate these token embeddings. Earlier, what did people do? They just took the average of these token embeddings and they called that as the single vector embedding. But people have been trying to understand if we store all these token embeddings, does it give us any fine grain? It has many fine grained information. Just averaging out loses much information. So there was this paper very recently. I forgot to cite that paper. So which said so queries also has multiple vectors. Document also has multiple vectors. You just consider something called as chamfer similarity score. Now I have to define a similarity score based on 2 bags of vectors, and that similarity score is defined using this. Each query token vector will go and find its best document token. Okay, so each query token QI will go and find the best document token, and you just add up their scores. That is the chamfer score. And people showed that this chamfer score is better at capturing human relevance than the single vector embeddings. So it's very beautiful. And to generate these multi-vectors, you need the same sized model. Because even earlier you were generating these multi-vectors, you just didn't store them, you just took the average. Here, nothing changed. But now the overhead is that you have to store all these vectors, which might not be suitable for like Bing, these web search kind of scenarios. So what we did was, we know from the lexical world, we know that not all query tokens are important. The word like the might not make much of an effect to define between the query and the relevance. This was a very popular method. There are very popular approaches in lexical search which handle this kind of things. They give lower importance to some common occurring words and they give higher importance to rare occurring words. So we introduced these weights which are dependent on the token IDs, and we saw that this over chamfer, over that earlier work, we saw some huge improvement on the Bayer data set. So average improvement is 4, but the highest could go as high as 14% improvement just by introducing these weights. Okay. So, and also we give a fast algorithm for this. let me quickly tell you what is filtered search. Filter search just means when you type shoes, now if you select a brand Puma, I only have to display you Puma shoes. That is the filter condition. So how do you do filter search? So this work, we have some nice theoretical guarantees. Again, we are able to come up with an algorithm using that theoretical understanding which we built for the naive ANN, but we still need to do experiments. Yeah. So coloring the nodes, it is equivalent to coloring the nodes, but there the diversity was a different constraint. Here filter has a different constraint. Here you are saying, oh, red node, if I give me filter condition says pick blue vectors, you should never output a red vector. It's different, yeah.
Diversity search, do I have to like predetermine how diverse I'm going to be? So like 2 colors or 3 colors?
Very, very good question, right? So the query dependent, you are basically asking about should the diversity be query dependent? Huh?
No, I just meant like.
Oh, okay. So you are saying you need to be the number of colors that need to be output, is that to be predefined? No, not necessarily. It just needs to satisfy that constraint. Out of 100, no product, you cannot have more than 10 items from the same product or same seller. That is the constraint. It can have 10. The maximum different colors it can have is 10, but it can also have 100 different colors, right? If everything is different.
So is that like a fact that needs to be decided when I'm building the
graph?
graph?
No. So
that's independent of the graph build?
No. So the build time, we all make sure that keeping this constraint in mind, we try to output solutions keeping this constraint in mind. If your relevant vectors are already diverse, then our algorithm will return 100 different colors. If the best 100 vectors are all of different color, then the constraint is trivially satisfied and our algorithm will return 100 different colors. But if relevant vectors, there is lot of commonality in the colors, then our algorithm will make sure that it will return just 10 different colors in that case. So it's dynamic in that sense. So hope I convinced you that large scale retrieval is a very important problem. And these modern applications are asking new things from this vector search. In my talk, I gave you some nice theoretical understanding of this, and some of the algorithms we came up for these new requirements are the first provable graph-based algorithms. So, by doing this, we have increased the wider applicability of these ANN algorithms. We presented provable algorithms with very promising experiments. So these are the references for this talk. Yeah, thank you. Yeah.
I had the impression that when we post a query, there are all these advertisements who bid to be shown.
Right.
In the higher bid. So that's very different from what you're saying.
Yeah. So you first, let's say the 10 products are being displayed. We first go and fetch 100 relevant things. And then on top of that, there is one more ranking stage which will bring down from 100 to 50. Among 50, there is a bidding, and we display the final 10. Yeah. So there are later stages which I didn't talk about today. But that first stage itself is not diverse, then you cannot hope the future stage to be diverse. So we have improved the diversity on the first stage. But we have noticed also that in the first stage, we have increased it by 15%. But in the final stage, we only see some 4 to 5% improvement in the diversity. Yeah, because in the middle, because Amazon, if it is paying higher reward, then we'll. Yeah.
So historically, people have motivated DPPs by using like literally the same applications of diversity in the search and diversity in recommenders.
So Jaguar example is a good example for DPP.
Okay.
So here I talked about diversity in ads. So the definition of diversity was slightly different.
Right.
But for that web search example, there they try to pick vectors which are nearby to the query, but they are some sense orthogonal to each other.
Right.
So that is the DPP process, right?
Yeah. So they use also. Like you don't design algorithms for that, but you could.
We haven't designed algorithms for that. I have only designed algorithms for the
color
diversity definition. So it's much more general than the color which I just talked about. But It doesn't handle the DPP case.
I mean, after applying the weights to the sample, I mean, instead of usual sample, when you are applying the weights to the sample, can you please
Yeah.
explain this average for person?
Yeah.
Yeah, yeah. So after applying the, yeah.
Maybe you need to speak to the mic.
So after applying the weights to sample, I mean, on an average, it's a 4% improvement is there. But in the highest, it's just 40%.
Yeah.
Just applying the weights to the usual sample, right?
Yeah.
And nothing else.
Nothing.
Okay.
Yeah.
That's
But these weights also we learn from the data set. We do a learning for these weights.
yeah. Okay. Thank you.
More questions?
Yeah.
Let's thank the speaker once again.